Okay, so here we are in section 4.6. We're talking about dimension of vector spaces. And just to remind you of a theorem that we talked about in the previous class, if you have a finite dimensional vector space, V, with a basis that looks like this, V1 through Vn, we showed that if you take any other set of vectors in V, let's say m vectors, W1 through Wm, then you get the following two facts in comparison. So if m is greater than n, if this set has more vectors than this basis, then this set will always be linearly dependent. If m is less than n, so if this set has less vectors than the basis, then it can't span your vector space. And so what that actually means is that if you have any set of vectors from V where the number of vectors in that set is different from the number of vectors in this basis, then there's no chance of this being a basis because it's going to fail one of those two conditions for a basis. Automatic consequence of that is that in a finite dimensional vector space V, in all bases that you could find for that finite dimensional vector space have to have the exact same number of vectors. It's worth pointing out that does not imply, in this case where our basis has n vectors, it does not imply that any set of n vectors is going to be a basis for V. There's going to be plenty of sets of n vectors that are not bases, but if a set is a basis for this V in this case, then you have to have these n vectors in it. Okay, so that's what this theorem says right here. So what that kind of means is that in any given vector space, there's a unique number that we associate with it, and that number is the number of vectors that would be in any basis for that vector space. We refer to that as the dimension of our vector space. And just to keep things consistent, the zero subspace for any vector space doesn't have a basis, so we just define its dimension to be zero. But we've already really encountered the concept of dimension without really defining it formally. For example, these vector spaces right here, Rn, Pn, the set of matrices, n by n matrices, all three of these we've looked at standard bases for, as well as other bases. But if you look at their standard bases, you'd see that Rn always has a basis of size n, so that's the dimension of Rn. Polynomials of degree n or less, any basis will have n plus 1 polynomials in it. And then we've seen this as well. This set of matrices is going to have dimension m times n, number of rows times number of columns for any matrix in that vector space. A lot of vector spaces that we've encountered also don't have finite bases. Usually they come in the form of function spaces, so the set of all functions on the closed interval a, b, continuous functions, n times differentiable functions, infinitely differentiable functions, polynomials with no restrictions on the degree, or the set of all sequences of real numbers. None of those have finite bases. We call those infinite dimensional. Okay. Now, moving down a little bit, one thing we've seen is that if you have a homogeneous linear system, the set of solutions to that linear system will always be a subspace of Rn, where by Rn I mean whatever Rn the solutions should live in. So what I mean here, or what we're looking at here, is a system with three variables, x, y, and z. Solutions for this linear system will look like ordered triples, so it's going to be vectors that live in R3. We're expecting the solution set to this to be a subspace of R3, and we're asked to find the dimension of that subspace, that solution space. So what I did is I solved this linear system using Gauss-Jordan. I set up an augmented matrix, row reduced it, and I ended up with this right here. That's a 1/5 and a -3/5 right there, if that's hard to read. When we end up with systems where we get this row of zeros down here, we end up with a free variable. So z is my free variable. I assign a parameter to that. So here I have z equals the parameter t. Plugging that in for the z's here and here, and then solving each of these two equations for x and y gives me y equals 3/5 t, x equals -1/5 t. So taking those solutions and putting them in the form of a vector right here, we know that that vector represents an infinite set of solutions. But that common value t is just a scalar. If I were to bring that out, this is a scalar times this vector here, -1/5, 3/5, 1. Even though there's only one vector here, I can think of this as the span of the, let's actually write it this way, span of the set containing just that one vector. Okay, and we've seen that sets containing only one vector are linearly independent by default. So this set, the span here, is automatically, the set contained in here, this one vector, becomes a basis for our solution space. So the basis that we're looking for is just the set containing the vector -1/5, 3/5, 1. Because there's only one vector in that space, then its dimension is 1. Okay? This is an important concept, and we're going to do this a lot. So solving a homogeneous linear system, getting its solution set represented as a linear combination of vectors. If we needed more parameters for the system, there would have been more vectors in this linear combination here. But the number of vectors that appear is going to become the dimension of that linear system, or that solution space. Okay, let's go ahead and move on. So this is a really important theorem that we're talking about next. It's called the plus-minus theorem. Let's just go through it really quickly. So we're going to be working in a vector space V, and we're going to suppose that S is a non-empty set of vectors in that vector space. There's two parts to this. So A, if S is a linearly independent set, and if you take any vector in V that's not in the span of this original set, then the set S union V is linearly independent. What that means is if I take this linearly independent set, and then if I'm able to find a vector V that's not in the span of that, I can throw that vector into this set, making it a larger set, and I'll still have linear independence. This part B here says that if V is a vector in S that's expressible as a linear combination of other vectors in S, then the set S minus V, so this is the set where we remove the vector V from that set, denotes, or I explained that already, then the span of this new set that we obtained by removing V would be the same as the span of the set if we never removed V in the first place. So in a sense, what this is saying is that if you're using a set to generate vectors using linear combinations, and if that set contains a vector that's already expressible as a linear combination of other vectors in that set, then this set is essentially unnecessary, meaning by removing it, we don't mess up the span of that set. Okay, so to prove this, for part A, we're referencing some non-empty set of vectors, so I'm going to give a name to those, v1 through vn, and then we're going to suppose that we can find some vector v that's not contained in that span. So what that means is that there's no way to represent this vector as a linear combination of these n vectors over here. Okay, so next thing I want to do, remember we're trying to prove linear independence here, so that means I want to take the set that includes all n of these vectors in S as well as this vector v, and create a linear combination of those and set that equal to 0. Okay, if we want to show that this is linearly independent, I need to show that all of these k's have to equal 0 if this is going to be true. So I'm going to handle this in kind of two cases. If k, notice that's the coefficient on the vector v, if k is equal to 0, then that term's going to drop out, and I'm left with just this linear combination here. However, this linear combination uses only the vectors in the original set S, which we assumed was linearly independent to begin with. So that implies that all of these k's have to equal 0. That's by assumption. So that step was pretty easy. Let's see what happens if k is not equal to 0. If k is not equal to 0, then we should be able to divide both sides of this linear combination up here by k, because we're not dividing by 0, and then we can solve that for v. You should be able to see that we end up with this linear combination right here. V is equal to this linear combination of the vectors that appear in the original set S. Okay, but that's actually a contradiction, because what we're saying is that v can be expressed as a linear combination of those vectors, which we assumed was not the case. We assumed v was not in the span of S. So this is impossible. that contradiction means that this assumption here had to have been false. K could not have been non-zero. So that brings us back to this case is the only possible case, and in that case, all of the k's are equal to 0. That shows that S union V is linearly independent. And that proves part A. Let's look at part B next. For part B, this time we're going to let S be the set including the vectors v1 through vn, as well as this other vector v. And again, just to remind you of what that vector v is, up here in the statement of part B, v is a vector S that is expressible as a linear combination of the other vectors in S. So coming down to my proof for part B, we're assuming that this v right here can be written as a linear combination of all of those other vectors. And I'm just going to give that linear combination in kind of a general form here. V is equal to k1v1 plus blah, 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 all that. Okay. Now we're going to let W, some new vector, live in the span of this original set. Okay, so what that means is that W can be represented as a linear combination of these n plus 1 vectors here. I'm going to let that linear combination show up right here. So I'm using C's for the scalars there. Okay. Now, if I take this V and plug in for V the linear combination that we're assuming V can be equal to, I get this. And then if I distribute the C into each one of these and collect like terms, so for example, I'm going to have a C1V1 here, I'll also have a CK1V1 here, I can combine those, giving me this term right here, C1 plus CK1V1. And I can do that for all of the vectors in this set. If you notice what happened, this shows that W can also be written as a linear combination of just the vectors v1 through vn. In other words, that v wasn't really necessary. I could get by with just the original n vectors. Okay? So what that means is that this vector that we chose from the span of S can be written as a linear combination of just the vectors in the set if we throw v out. So that means that this vector W is in that span. Now, if you think about what I'm trying to do here, I'm trying to show that two sets are equal to each other. So again, coming back up here, I'm trying to show that this set is equal to this set. And the way that you prove two sets are equal to each other is you show that every element in one set is contained in the other, and then every element of the other set is contained in the first. So you have to show kind of subset inclusion both directions. We just showed that any element of the span of S is going to be contained in the span of S minus V. Okay, so that means we've gone one direction. We have to go the other direction now. So now, if we choose a vector in the span of S minus V, we now want to show that that would also belong to the span of just S. That's actually easier to do. So if W is in the span of S minus V, then that means W can be written as a linear combination of just the V1 through Vn vectors. I wrote that out here. Okay. Now notice if I wanted to, I could add a 0 vector to this and not change anything. So plus 0, that's the 0 vector. And we also know that that 0 vector can be written as the scalar 0 times the vector v. But what we just did here, even though this is equal to 0, we showed that W could be written as a linear combination of all the vectors v1 through vn as well as the vector v. That's the original set S. So that means W belongs to the span of S as well. So we've gone both directions. The conclusion now is that the span of S minus V is equal to the span of S.